Go ahead and hit record. Any general questions? You guys all perfectly understand.
I was muted. I don't have any questions, but I'll start the lab after this.
You have a microphone, Eli, that has a lot of tinniness to it. You know, you sound like it's almost like disguising your voice or something. It's very tinny and very hard to understand.
I've heard that before too. It's like right up against my face. I don't know.
No, it wasn't that way at the beginning of the semester. Okay, so let's go ahead and pull up our lab. Close this. Now I just recently realized, as in the last 20 minutes, that there were some initial typo errors, at least on the front page. I can't tell you about other typo errors that are in there. One, this said lab 4, it now says lab 5. One, it said it was due the 20th, even though we were taking on the 22nd, and now it says the 29th. So if you happen to have already downloaded the old one, that has been fixed up some. There we go, that's better focus. Okay. So this week's lab, we're going to take a look at some of applying Newton's laws. Some of this is more from chapter 4 of the book. And I think I'm going to be changing, I'm going to have to rewrite a new lab for next week. I think I want to do a different lab as well. But basically, we're going to look at applying Newton's laws where there is an applied force, friction present, both static and kinetic friction. There's walls present, which really isn't part of the lab. I want to ignore the walls themselves. They will be a stop on things, okay? And you can look at the sum of things. So the simulation, there's a couple different ones. Simulation 1 is, I think we're just using force of motion. I think I ended up not using the ramp on this, but I'm not positive. If we go down the first one, I ask you to open up the simulation number 1 above here, which is forces and motion. Now I encourage you guys to go to this site. It's the PhET Interactive Simulation site developed by University of Colorado. It's first started by an individual named Carl Wyman, who actually, I think, put a lot of his Nobel Prize money into getting the thing started. But I'm not certain of that. Okay, and there's a batch of different simulations on it. Now, when you go to these simulations, they have different modes. They have a mode that works through different HTML, something called ChirpJ, or a lot of them also have Java. There used to be a lot of Flash, and the Flash is no longer supported. The Java often is an easier way to use the simulations. At least I find it that way because they actually download onto your computer. Okay, the others are all internet-based. Now I just use the forces and motion here. Now there's a few different forces and motion graphs. There's Java via, and you have to look at which ones you're looking at. So I'm going to go and find my force and motion graph. And this chirp J is some sort of Java interface, so it runs on HTML. But I find that that runs a little bit slower. And this is just some piece of information that you can download these Javas direct onto your computer and work on your computer, and they can work a little bit smoother that way. I've got a chat here. In the right corner above the question. Not sure what that is. Not sure what you meant by as long as you click on the right corner above the question. Okay. So I have the simulation up here at this point. And there's a batch of different aspects of it to it. On the force graphs, that's the one that we're going to be looking at for. There's a different graphs we look at. The first thing we'll be looking at the force graph. You can also look at directly at the friction graph, where you can modify static friction, kinetic friction, your object mass, and gravity as acting. On your force graphs, you don't get as much aspect to that, but you can get different graphs to them. There's F applied, F friction, F of the wall, and F sum. And they're all shown on a single graph. So if I hit go, see everything is here at the bottom. Now, if I start pushing this thing.
Can't see the graph, you can't see the simulation.
All right, thank you. Now you should see my screen.
Yep.
Now you have my screen up. We'll just reset this. Okay, so we've opened up the screen here, and there's force graphs over here. And clear all this and reset all. And you can show different graphs on here. I can show the force applied, the force of friction, the force of the wall, the force sum. Now the walls in general, I don't care about. Now there's going to be a question on here that asks about if you hit the wall, you want to ignore when you hit the wall. In terms of most of the questions in here, they're going to tell you that when I say at the wall, that's right before hitting the wall. You see here, this starts putting out the green line, and that's because all the friction, all the forces are the same. They're all zero. I start pushing this. See here, my force applied keeps going up. I'm going to pause right here. It went back down to zero, but you see here, my force applied and my force of friction were of equal magnitude, opposite in direction, and my force sum stayed zero. And I'm just going to turn off force the wall. There I go some more. And ever increasing that force applied. Look what happened here. I'm going to try to do this a little bit slower. Just back this way. Let it stop. It's going to come to a stop. I'm going to clear the graph again. Now I'm going to start applying a force this way. A bit more, a little 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 bit more. And look what happened right when I got to that point. Now it's accelerating. And then I let it go. Okay. Now look what we have here. Green is the net force. As I keep applying this force, the force of friction keeps going up. Okay, this is the absolute magnitude. So I'm looking at the magnitude. It's a negative, it's in the negative direction. I could have been pushing this way, in which case the force applied would have been down and the force of friction would have been up. But it's opposing the force that I'm pushing at. This is, and it's not moving. There's no net force. But my net force is 0 and it's not moving. Now, if I look at my acceleration graph, with a plus here. Okay, maybe I can't do that when it's paused. There's my acceleration graph. Zoom in on here. We'll pause it again. If I look at my acceleration graph, it's of course 0 everywhere because my net force is 0. Now, all of a sudden, with a very small change, right here, I made a very small change. You can take a look here. There's this right here, you can see we have 0 net force. Now I make a little tiny change in my applied force, but my net force makes a big change. And that's because we overcame static friction and went to a region of kinetic friction. The kinetic friction is now a solid line, and it's independent of the applied force. And in fact, when I let go, my applied force here, let me turn off the sum, my applied force goes to 0, but friction, my kinetic friction stays constant. So as long as the object's in motion, kinetic friction is present. As long as it's in motion, doesn't matter if I'm applying a force or not, kinetic friction is present and it's always opposing the direction of motion. If I look at F sum here, because I had an applied force greater than the kinetic friction, I have a positive net force or sum of forces. As soon as I let go, my applied force here dropped to 0. And so the sum of forces is just friction. So now it's gone negative and is causing it to slow down. And that's the same thing that happened in the acceleration graph. Right here, when a force went up, acceleration went up. When force went down, then, and when the force was removed, the acceleration switched signs. Now, if I look at, and play again here so I can turn on the velocity graph. If I look at my velocity graph, as long as I'm applying this constant force and the acceleration is going up, I get a nice increase in velocity. But the velocity is always positive. As soon as it goes, my acceleration goes negative, my velocity doesn't go negative, but it starts going down up until it comes to a stop. As soon as it comes to a stop, we're back in the regime of static friction. Okay, so my friction force drops to 0 because it's at a stop, and the static friction depends on the applied force. The magnitude of the static friction depends on the applied force, all right, up to a maximum value of mu sub s times the normal force. So it has that maximum value. And we've discussed that a few times. That was in the past stuff. So I ask you in here to show these 3 graphs, choose the small graph and move it all the way to the left. I'm going to clear my graphs here. I'm going to move it all the way to the left. And it hits the wall here. And that's an extreme event. Pause it, clear it. I want you to check the sum of forces box and the vector attributes on the right-hand side of the screen. So here's your vector attributes. You can also click sum of the forces here. Okay, and my simulation lets me show a free body diagram. So here's a free body diagram. The only forces present right now are the normal force and the gravitational force. I start pushing on it, and I get a force of friction and an applied force. Force of friction, and it starts going. Now, as soon as I broke through the static friction, started getting kinetic friction, I got a sum of forces. Now, when I let it go, the sum of forces is to the left, opposing motion. I'm going to pause it, play back, and watch the force diagram here. So my applied force is increasing and my friction force is increasing. They're equal and opposite. Up to a point, all of a sudden I broke through static friction, and now I have a sum of forces. And this force is now constant. So when I let go, this force won't change. Okay, so let me repeat that. Reset it and play back again. Some of the forces come on, and my sum of the forces is pointed to the right, because I'm still pushing. Pushing, pushing, pushing. Now I let go. Notice my friction force never changes at this point because it's all kinetic. And this is the free body diagram as we go through it. I've got a free body diagram. So here's my free body diagram, and my friction force and applied force are matching my gravitational normal force. Okay, I keep doing applied force. My friction force keeps increasing, my applied force keeps increasing. I keep going, and all of a sudden, right here, where I jump in, I start accelerating, and now I've hit the curve. I still have a friction force and applied force. Notice I'm not attaching this sum of forces to the body itself. This is just up there to show you what it is. But a sum of forces doesn't really attach, you don't really attach that to your free body diagram. You want to attach the individual forces to your free body diagram. And we continue on. So we ran through that. And basically, I think the first part of it, just to check the sum of force box and vector attributes. Click the button and okay, click the play button and then click on the box and move it back and forth. So you can actually just click on the box and move it back and forth. And this is just for you to get used to it. You look at the applied friction, your acceleration graph. So basically what I just went through, and you're going to do the same thing. Now you can also pause the simulation, which is important, as that is key to the simulation that we're going to run. So I just note I just did it between I do not have the acceleration and velocity graph. I also have a position graph I can turn on. I have to be actually running to turn these on. My position graph is on. And this shows where my position is. In negative position, I'm growing in position. You can see here that this is growing in position nicely because in a nice smooth curve here, but it's a changing curve because I've got an ever increasing velocity. So the slope is changing. The slope at any time equals the slope of my velocity curve. And then I go into right here, my slope changes sign. I have a negative curve and I've got a negative velocity, a negative slope of my velocity graph. And this is just the acceleration. So the slope of this curve is the level of my acceleration. Now, we can type values into the force graph. So we're going to clear all this. So we're going to put 100 into the force applied. Okay, and we're going to tap the play button and we're going to run for about a second. So there's about a second. Then you're just gonna tap 250 in. We'll run for about another second. It can be a little bit longer, nothing special about this. I'm gonna tap 400 in. And you see at each one of these, the force of friction is balancing the force applied. We're still in static friction. Okay, I'm gonna tap 450 in. And it's still following that. And I'm gonna put 500 in. And now, because I know in advance, it's gonna, my applied force is gonna go up, but my friction force is gonna go down. Okay, and we're gonna start accelerating. So you basically see this. And we get a sudden drop in friction. So why did the static friction keep increasing up until you applied 500 newtons and then suddenly drop to 294 newtons? And this is magnitude. It says minus 294. What is the maximum applied force allowed before breaking static friction? Now, that you need to calculate. Over here, in this, it tells you the coefficient of static friction is 0.5 for the small crate. So you can calculate what is the maximum applied force before breaking static friction. We talked about that today. What does the friction drop to once static friction is broken? Well, it's a kinetic friction and it's 294. Now, when I go on this box, this is one of the reasons to have done this only 1 second each so that I had more time. So I've really gone too long here because I made 1, 2, 3, 4 in 6 seconds, 5 and 6 seconds. Well, I really wanted you to only be covering 3 seconds. And notice I've moved a lot of distance here. So I'm going to repeat everything I've done. Run this back to 0. I'm just giving it a good hard push. Look at about what's that?
Does the coefficient of the static friction, does it, or does it only show when it moves, or do you have to set it, you have to go back to it?
One more time. I don't understand what you just asked.
The small crate, the friction coefficient that's 0.5, is that when it breaks only, or is that you setting it someplace? Like you set the
Static friction is a constant. It depends on the materials in contact. It's a constant. The coefficient of static friction is a constant. It depends on the material. The static friction depends on the applied force. The static friction opposes the applied force. So it can never be greater than the applied force. For instance, now I clear all this again. Okay, I'm going to type in 0 here. So I have 0 applied force, and hence my friction force, when I put in 0 here, and I run again, run and pause, okay, my friction force is 0. Okay, all because this, and these are the parallel forces. Forces parallel to the normal. Okay, the normal force is perpendicular. We're looking at the parallel forces here. I have an applied force. That applied force, I ask you to start at 100 and run it for 1 second, thereabouts. Don't make it much more. So you put in 100. And we ran it for about 1 second. And nothing moved. Okay, note that the friction, which is the static friction, is minus 100 newtons. Applied force is plus 100, so the friction is minus 100. We went to 250. We went for about another second. We went to 400. And we went for another second. So we had pause and then play. Pause it again. 400 newtons applied, minus 400 newtons from static friction. It's never greater than the applied force, and it's never greater than its maximum value, which is mu sub Sn. Mu sub Smg, if we go calculate here, for this small crate, for my small crate, this answers one of your questions on there. Mass equals 100 kilograms. Mu sub k is equal to 0.3, and mu sub s is equal to 0.5. Okay, these are constant. These depend on the materials. Those never change. My coefficient of kinetic friction when it applies is equal to mu sub k n. N, in my free body diagram, we're not moving in y, we have n and mg. So n just equals mg, which in this case is 0.3 times 100 kilograms times 9.8 meters per second squared. And that's equal to 294 newtons. The sign of Fk depends on which way you're pushing. If I'd been pushing to the left, this would have been positive. Okay, it always opposes motion. I'm trying to give motion to the right. The man here is trying to give motion to the right, and static friction is opposing it. F sub s max is equal to mu sub s n, which is equal to 0.5 times 100 kilograms times 9.8 meters per second squared, and that's equal to 490 newtons. So I can plug 489 in here, 489.9, and run. You see, it's still not moving. 490.1, and it starts moving because I've broken static friction and I'm in the regime of kinetic friction. Very important to know when you're in those regimes. We'll clear all this. Let me just show you that. Clear everything. So we're clear on this, that it's always opposing motion. Okay. Let's do this. We'll clear the graph. Not quite sure why this is happening this way. And then is to affect the simulation here. There we go. And there we go. So pause it. Let's clear everything. Okay. So if I start pushing it this way, you get a force, a force, a force applied, a force applied, a force applied. Eventually, I get a sum of forces. You see here, my friction force was positive because my applied force was negative, but it's still matching in magnitude. We're matching in magnitude up to the maximum applied force. I ask you to start from the right. And we'll clear everything. We'll set the applied force to 0. And clear my graphs again and pause it. Okay, so I'm just running through these. So now we're going to go and we're going to do our 100 here. We're going to do our, I think I said 250, right? And then I'm going to go to 400. Run that here. We're going to go to 450. Show that it's still not moving. And then we're going to go to 500. Now the key here is don't let it go past about a second, because you just don't want it to go too far. So now I'm going to play and only give it about 1 second. Okay, so I don't want it to move very far, which is why I don't leave it on for a very long time. So I want room on this rest of this room here. Okay, so you see that we have a drop in our magnitude of our friction. You guys were in kinetic friction. Now we're going to start reducing. Now over here, when we were at, now we went to 500, but when we were at 350, the object wasn't moving. And it was no longer accelerating, and it's not accelerating. What's going to happen when I drop it to 350 right now? What do you think?
It'll just go back to that level on the other side,
What level?
where you stopped it at. It'll just go back.
Here was 350 before, here's 350 here. So this was 100, 250, 350, or let's see, it was 100, 250, 400. So this was 100, 250, 400, 500. So is it going to go to here? Is it going to go somewhere between these two, or is it going to go to here? Is it going to stay here?
It should go back to that level where we what did you say, 400? It should go to the level where 400 is.
Yeah, let's suppose I drop it to 400. Do you think it'll go to the level 400? But it's moving. The object's moving.
Oh,
So,
yeah.
and so since it's moving, only kinetic friction applies if it's moving. Static friction doesn't apply if it's moving. So I'm going to be above 294, so I'm still going to be accelerating. So here's my acceleration graph. I'm going to drop it to 350 now and run it for about a second. So look here. I dropped it to 350. My friction force didn't change. My net force dropped, but it's still above 0. My sum of forces dropped, but it's still above 0. Because it's moving, we're in the regime of kinetic friction. You don't just automatically switch to regime of static friction. It's in the kinetic friction regime. So as long as it is moving, kinetic friction applies. It has to be stopped to have static friction apply. This is why when you push a box across a room, getting the box started is harder than keeping the box moving. Okay, so I dropped it to 350 and it keeps going. And what does the friction force drop to? Once static friction is broken, well, you can just read it off here. That's the friction force. And tap and run, I ask you to tap and run it until you hit about 0 meters. So that's right here. But that's it, tap and run it to about 0 meters. And that's about 0 meters. It's not quite, but it's close enough. So here's my position. Here's my velocity. My acceleration went down, but I was still increasing velocity. Now, what's going to happen when I type in 294? What do you suppose is going to happen when I type in 294? Araceli, Anna, you got an answer for me?
IDs continue moving.
It'll continue moving. Will it continue accelerating?
Yes.
It'll continue accelerating or just continue
No,
moving?
no.
Okay, because at 294,
Stop.
applied force matches my friction force and my sum of the forces will be 0. But it'll keep moving. Okay, so this went to a flat line. Right here, we went to a flat line. See here, this went down to 0.
Mhm.
My acceleration went to 0. My net force went to 0. See here, sum of the force is 0, acceleration is 0. My velocity, though, was still constant. And then we're going to go back. And I say till it reaches about 4 meters. I say to run this till it goes to about 4 meters. That's close enough right there. Now I'm going to go to 0. Now when I go to 0, what's going to happen to my applied force? It's going to go down to 0, right?
Yep.
What's going to
Yes.
happen to my friction force?
You go to the same place.
It's going to stay at the same place, right? The box is still moving.
All right, I see. Yeah.
My sum of my forces is going to go down because now it's just friction force acting. So the sum of the forces should now go down to match a level of my friction force, because that's going to be the only force happening. So the green line should go down to the red line here. What's my acceleration going to do?
Go down.
Go down. And so my velocity should start dropping. And we're going to run it till it stops and then run about another second. Okay. So here's my set of data. Okay, you can see here from my applied graph, if I get rid of my acceleration, velocity, and position graph. I don't know why I can't get rid of that one. Okay, so there I have just my force graph. I kept applying forces until I got it moving. Okay, and it got moving. Then I lowered my applied force to that 350, but I still had a net sum because I had 350 that was greater than minus 294. Then I lowered it to 294, so they're matched, so my sum is 0. And then I lowered my applied force to 0, and I still have my static friction applied, and I have a net force below 0 and equal to the not static friction, still apply kinetic friction, and I have kinetic friction up until it comes to a stop, at which point it's back in the regime of static friction, but there's no applied force. So the static friction is 0. Maximum static friction is still mu sub Sn, but the applied force is 0, so the static friction is 0. Friction, F sub S is less than or equal to mu sub Sn. F sub S max equals mu sub Sn. F sub S is less than or equal to mu sub Sn. F sub S is equal to F applied. As long as F applied, the net applied force is less than or equal to mu sub Sn. So it equals F applied, which F applied or F net. We only have one applied force in this case. This is F applied, not F net, because F net has Fs in it as well. So it's F applied as long as F applied is less than mu sub Sn. Once F applied goes above mu sub Sn, the object starts moving and we're in a regime of kinetic friction. Very important to remember this. Okay. Now if I look at my acceleration graph, we note that it has the same shape as my sum of my forces graph. Note this has the exact same shape, as it should. Net forces mass times acceleration. Okay, there's a scalar difference between it. The units different between it. Okay, my velocity, well, it was 0 until I started having an acceleration. If I turn off my force graph, I've got no acceleration here. I start at rest, we stay at rest. I add some acceleration, I start getting an increase in my velocity. I change the level of my acceleration, I still get an increase in my velocity, but the slope has changed. I drop my acceleration to 0, same as dropping my force to 0. My velocity stays constant. Now I go in negative acceleration. That's when my applied force went to 0 and only kinetic friction is going. My velocity starts dropping. The speed starts dropping. The magnitude of my velocity starts dropping until I hit 0. Now static friction's in play and we're at 0 velocity. And the position graph isn't so important for that. And you can keep watching these on your free body diagrams. Okay, now. This one asks, some of these questions are actually repetitive. They're just repeated in a different way. Why is there no net force until 500 newtons is applied? Okay. Newton's third law states for every action, there's an equal and opposite reaction. Okay. So I push on the block pushes back on me. The block through friction pushes on the board here or the sidewalk pushes back on it. Friction force is opposing motion. So going through them, anything that was trying to move one way is getting pushed back on this way. So if you were to try to carry this around through everything, here's the block. Now it has an F applied. And it's below static friction. Okay. Here is friction. On the table, there's friction. This is the sidewalk on the block. This is the block on the sidewalk. Okay? So we have two different ways of looking at this. So the sidewalk is pushing back on the block at the same level of F applied. This can't be greater than that. Okay? Or friction would be making the block move. Ask you to calculate the maximum static condition. Was that zero net force? Well, we already did that, mu sub Sn. There's a magnitude and direction of the friction force when it's moving. That's the kinetic friction opposite to the direction of moving. Force that needs to be applied needs to exactly balance the kinetic friction force. Okay, so you've got a batch of skills now that you've learned. Okay, there's a mystery object. So this one you're going to need to do on your own. There's a mystery object here. Okay, I have a mystery object. Now, I ask you to find the mass, the coefficient of kinetic friction, and coefficient of static friction. Okay. Now, let's just take a look at something here. We're going to clear everything. We're going to put it back right around to zero. Let's put it over there. Okay. You can get to these numbers quickly. Okay. You can find you can get a couple numbers quickly. So let's just get this guy started moving. Okay, so it's moving now. Now it's slowing down. And it hit the wall, but that's okay. Because now we pause it. And we go to playback. Right here, we have kinetic friction acting because the object's moving. We have velocity. Okay, so the object's moving, it's kinetic friction. We have a value for acceleration. So F, which is equal to mu sub k times n, it's equal to mu sub k mg.
Teacher. Please
Like
move.
that,
Thank you.
has to equal to the mass times acceleration. Mass cancels. So my acceleration is equal to mu sub k g. You can measure the acceleration. And mu sub k is equal to a over g. Okay, so now I can get the coefficient of kinetic friction quite readily. I also know So now that I have the coefficient of kinetic friction, this also gives you the force, 241. So A was equal to minus 196, 1.96. So the magnitude of A is equal to 1.96 meters per second squared. So I can get mu sub K. I also know that my magnitude of F is equal to mu sub K mg, or it's equal to m times A, either one. I've got my force, which is my force of friction, of 241.08 newtons. And with a minus sign, and that's equal to minus m, is equal to minus m times 1.96 meters per second squared. So m equals just F over A. So m just equals F over A. You have the values. This is the sum of the force in A. So I can get m really readily. Now, static friction is a little bit more difficult to figure out. You might have to use the experimentation to figure that out by creeping up on it. That's one way that you can do it. You can creep up on it and say, where does it release? Now, to do that, you've already done, you now know the mass and you know the coefficient of kinetic friction. You clear everything. We run the forces to 0. I need to actually wait for my box to come to a stop. Pause. Put my box back towards the beginning and clear my graphs. Okay. Now you can walk up on it to figure this out. 200. 300. 400. Well, it's somewhere in there, so I pause it and I have to wait for it to come back to a stop. It's between 300 and 400. Let it come to a stop now. Came back to a stop. 350. Still not enough. 360. Still not enough. Acceleration didn't go up. 370. Oh, that was enough. Pause it. Go back to 0. So it's between 360 and 370. Let it come to a stop. 365. That's more than enough. So it's between 360 and 365. So 363. Oh, I didn't let it come to a stop yet.
68.
Now, that's one way to do it. Or once it was running, I go 400. Oh, I can't do it that way. 363. So let me go to 0. Comes to a stop again. 363. Too much. 0 again. Comes to a stop, 362. Too much? 0 again? What are these things? 361. That won't do it. I now know it's between 361 and 362. You guys need to get the rest of the way there. And you need to pay attention to what I was just doing, but we're zeroing in on it. I went too high, then too low. Okay, so I zero in on where it is. I know it's between 361 and 362 because if I do 362 right here, and I can just watch my acceleration graph. I don't care about this graph. I could turn this one off and this one off if I want my graphs bigger. Okay. But basically, when you're doing this, you want to find the point. You also show what the zero sum is. So by just watching the acceleration graph, I can determine the force required to move it, which gives me a measure of my static friction. That's just a mystery object. You got to go figure out the coefficient of the mass and that. Now we're going to use, at this point, we're going to use simulation number 2. And what we want to do is I want you to calculate a few things, and then I want you to verify it. So you have, I'm going to make this problem a little bit easier. I'm going to set mu sub k equal to mu sub s equal to 0.4. We're going to set them equal. Okay. Now, what is the maximum ramp angle I can put a mass at? M equals to 150 kilograms, which turns out not to be irrelevant. Oh no, I did not say mu k and mu s equal to 0.4. I set mu s equal to 0.4 and mu sub k equal to 0.3. Now this is at rest. So at rest, place it at rest. What is my max angle, theta max, that my ramp can be at? Now clearly 0 is good enough, right? If we go in ramp, open up simulation number 2. Here's simulation number 2. It's called the ramp. And I've got a point one on here where I can set friction. And we leave gravity at 9.8. I'm going to set the mass of the object equal to 150. I'm going to set static friction equal to 0.4. I'm going to set kinetic friction equal to 0.3. I'm going to put the angle of the ramp way down. And we're going to start with the object way over here. Now, we're also going to look at our free body diagram. Okay, and our sum of forces. Now, this doesn't have a bunch of graphs on it. We can go to force graphs, but the force graph doesn't let us independently change these. Okay, so we'll get force graphs here. I can't independently change static friction, so I need to look and see if I've got an object with a 0.4 static friction. So I could just use the textbook from the force graphs because it has one, but I don't have a custom object. Here I have custom, I can set them custom. And I just start increasing my ramp angle. There's force of friction, a vector on it. I go to 20. I go to 30. Now see, I have a sum of forces. Okay, so when I was at 20, right now I haven't hit play yet. It's not doing anything. If I do this, it doesn't slide down. At 30, it starts sliding down. And you see I get sum of forces on there right away. Now note my free body diagram. I've got F sub n perpendicular to the surface. I have force of friction parallel to the surface, and I got the force of gravity straight down. Now, you should be able to draw the free body diagram just like it does Fg n F friction. We want to find the angle. So here, I'm going to set X and Y. Sum of the force in my Y direction is going to equal to N minus mg cosine theta. That reset equal to 0. So N equals mg cosine theta. Sum of the force in my X direction is equal to F sub X is in my positive X direction. Okay, so my force of friction, that's the F static, or force of friction here. Because I want to find the maximum angle that I can set it at. So F static minus mg sine theta equal to 0, and I want F sub s max. So this is equal to, because I'm looking for the max angle. So the max angle, the more I increase this angle, you should see that the larger F sub f is going to get. If I draw my ramp angle at 20 degrees, look at my vector size when I hit 20 for F sub f. If I go to 10, I need to go down. Okay, so let me hit play here, because I really need to get it back down to, got to come to a stop again. Okay, I had to have it come to a stop again. So we have it coming to a stop again. If I go to 10, here's my vector size for my force of friction. If I go to 20, this length of that vector should get about twice as long. Not twice as long, but how much more is into the gravitational. So it should get longer by the ratio of sine 10 degrees versus sine 20 degrees. Because that's the coefficient, that would be gravity. This is n sine 20 over n sine 10. This is the gravitational force that the friction force is opposing at the two different angles. So if I do on my calculator 20 sine 10 sine, divide, it should get about twice as big. So this vector should get about twice as long. So let's type in 20 now. And notice that got about twice as long. So you can use these graphs to see what it's doing, because it's drawing your vectors in a reasonable amount with regard to the actual forces. So it made this force twice as long as the previous force. Okay. So the more that I drive it up, now the maximum that this can get to, though, then is F sub S max is right when it breaks through. So F sub S max equals mg sine theta. But F sub S max is equal to mu sub S n. Is equal to mu sub S mg cosine theta. So if I want to keep it from sliding down, my sum of the force in the x direction is mu sub S mg cosine theta minus mg sine theta. My m and my g cancel. That has to equal 0, and mu sub S just equals tangent theta. So if you know mu sub S, you can calculate the maximum angle.
I have a tutoring session I want to go to for this. I'm going to log off.
What's that?
There's a tutoring session I have at 12:45 that I want to go
Okay.
to for this.
All right. So that's what you're going through on this one. That's the ramp. Make sure I'm get through everything we want to get through here. So that gives you the ramp here. So you can do the calculation. You're going to validate it. And then you're going to set the angle to the nearest 1/10 of a degree below the value you calculated and show that it's not moving, and 1/10 of a degree above the angle that you calculated and shows that it begins moving. You're going to verify your calculation. If not, you better repeat the calculation and get reasonable agreement. Now, I want you to calculate the applied force that you need to apply such that you can raise the ramp angle to 40 degrees. So now, your free body diagram is going to have the force of friction. You're still going to set it at the max. You're still going to have the normal force. You're still going to have the force of gravity, but you're also going to have, you can draw it over here, F applied, or over here, F applied. I don't care. Choose which one you want to draw it, either here or here. Okay, but choose which one you want to draw it at. So if I draw my free body diagram, I'm going to draw them both on the right. I've got my normal. I've got FG. I got 40 degrees. I have F applied, and I've got F friction. Okay, or that equals F static max. So I want to know the minimum force that needs to be applied so it won't move. This is the minimum force. So the sum of the forces, here's X and Y. Okay, the sum of the forces in the Y direction is equal to N minus mg sine 40 degrees. Sum of the forces, or it should be cosine, sorry. cosine 40 degrees. Sum of the force in the x direction is equal to F applied plus Fs max minus mg sine 40 degrees. This is equal, this then leads to F, and that we want to set equal to 0, just barely. So FA is equal to mg sine 40 degrees minus Fs max, which is equal to mg sine 40 degrees minus mu sub s mg cosine 40 degrees. Okay, so that just says how much has to be applied to keep it from sliding down the plane. Now, let me ask you a question. Now I'm going to apply a force over here. And can I do that? Yeah, I can apply a force here. Let's just set it at 150 newtons. And let's see if that's enough to keep it at 40 degrees from moving. Nope. Pause. Let's see if 800 newtons is enough. Well, now I'm pushing it up at least. So it's slowing down. Now I'm going to move the position just for fun. This just moves the position without changing the forces. Okay, so is 800 newtons the minimum force required to keep the block from sliding down the plane?
No, because it still slides down. It's still sliding down. It
Oh,
just
It's
slowly.
it's not sliding down right now.
Oh, I thought you had it on pause.
No,
In that case, yes, it looks like it's the minimum applied force.
so if I put 790, it should start sliding down. It's at 800 right now. So if I put 790, you say it should start sliding down.
Yeah,
Okay, so
you can
let's
try
see.
it.
Let's see. Didn't start sliding down. Still stationary, didn't start sliding down. How about if I put 700? Do you think it'll start sliding down then?
Mm.
It still didn't start sliding down. How about 600? But it's not moving up either. It's still not sliding down. How about 500? It's still not sliding down. 400. Now it's sliding down. 800. Now I'm going to move its position again. But it's not going up either. Now look at this little red arrow. Look at the way that it's pointed. It's pointed up. So let's make this a little bigger. Let's go to 600. It's still not sliding down. My F applied got smaller. My force of friction got less. There's force of gravity that's acting this way. There's a portion acting this way. So if I go to 700, my force applied is going to go up and my force of friction is going to go down. They're both going to be working to balance it. The friction doesn't have to work as hard because I apply more force. If I go to 700, force of friction went down. If I went to 800, force of friction went down more. Suppose what's going to happen now if I go to 1,000? Is it going to go, is it going to, what's going to happen now?
The
What would
force,
you-
I'd say that the force of friction keeps getting smaller as you go up in applied force.
Oh, so look at here, Rhea, as I keep going up, the force of friction is going to keep getting smaller. I'm going to put in 12, I'm going to put in 1,200. Oops. I'm going to go back to 800. I'm going to change my position again, so it's up a little bit. I'm going to put in 1,200. Now, right here is on this red here is my force of friction. Okay, right here is my force of friction. Now I'm going to go to 1,200. I was at 800. I have to still hit enter yet. The magnitude of the force of friction got bigger, but it's now in the opposite direction. So now friction, now gravity and friction are working together to keep me from pushing it up. I go to say 1,300. I go to say 1,400. Now I start pushing it up the ramp. See what's going on here? There's a big zone because friction always opposes motion. So when I was applying some force, but not enough to overcome the force of gravity, friction was doing work, was putting in effort as well to keep it from sliding down. At some point, I even drive that down to 0 friction force required. But then as I increase the force some more, all of a sudden I've got my force applied is more than the force of gravity. And now friction opposes motion going up the plane. Friction always opposes motion. If there's more force going down, friction opposes the object moving down. If there's more force, some of the other forces going up, friction will point down the plane. The force mg is always down the plane. Mg sine theta is always down the plane. F applied is always up the plane. If F applied is bigger than mg sine theta, then the force of friction will be down the plane. If the force applied is less than mg sine theta, there'll still be a coefficient of friction pointed up the plane so that it's opposing it going down the plane. Okay? Always opposes motion. So there's a big band of applied force where the object won't move. Just like on the flat, if I had a object on a flat surface and I want to move it to the right, I have to put a force applied to the right. And it has to be greater. My force applied has to be greater than, to get it started, mu mg. That's to get it started. That's to be greater than mu mg. And it's positive because it's to the right. But if I want to go to the left, I want to start moving this way. I got to push from this side. F applied. And my F applied magnitude has to be greater than mu mg. And the magnitude has to be greater than. So I have to have a bigger force applied than mu mg, but now it's negative. So I'll get no motion if, so what I want to do is F applied, that is less than mu mg and greater than minus mu mg, it won't move. There's a big band where it won't move. This entire regime, box will not, mu sub s, box will not move. So now I'm actually talking, I'm not using the absolute magnitude of F applied. I'm including its sign. The negative is to the left and positive to the right, but I have a big band of F applied where it won't move. That same band is going to exist on a ramp. It's just going to be offset around 0. It's not going to be at 0 anymore because mg is in place also. Okay? That all makes sense? Think about it some. That completes the lab introduction, which was long, but you should be able to get to the lab pretty quickly at this point. Learn to draw your free body diagrams. They are critical to solving problems.